So good morning. Thanks, Professor Bento, for the introduction. I would like to welcome you all to the webinar 5, Geotechnic, General Rules and Seismic Action. So this is the second seminar, and so my name is Christoph Butenwig, and I'm from FH Aachen University of Applied Science, and I will join the session together with my colleague Linde Köber from the Technical University of Civil Engineering in Bucharest. So we would like to welcome all of you, and I think this will be a very interesting and important webinar with a lot of information given by the speakers. The seminar is constituted by 6 lectures and coordinated by Alain Pecker and Kyriazis Pitilakis. And we will have 25 minutes for each speaker and 10 minutes for questions. Just a few information more. So after each presentation, we will have time for 10 minutes of questions. And you have to type the questions in the chat, and we will follow the chat, and then we will proceed the questions to the speakers. And if we have too many questions, do not worry about it. So we will monitor the questions, and if it's not enough time, we will contact you together with the speakers and answer your questions. And please make sure that you identify yourself so that we can send you the information to your questions. The seminar will be opened by the first presentation given by Professor Alain Pecker. It is the general overview of EN 1998 Part 5, Basis of Design and Seismic Actions for Geotechnical Structures and Systems. I will introduce the speaker shortly. As you see, Mr. Pecker is a really highly and well-known, recognized expert in geotechnical engineering. And he was leader of the PT5 for the evolution of the part that is going to present today. He was the president of the French Society of Soil Mechanics and Geotechnical Engineering. And he is also the honorary president of the French Association on Earthquake and Earthquake Engineering. So today he's an independent consultant and professor at École de Pont Parité. And he's also involved in many teaching obligations at other universities, as you can see on his short CV. So now it is a pleasure for me to lead over the floor to Professor Pecker and his presentation. And please, Alain.
Thank you very much, Christoph, for this introduction. Okay, I will share my screen. Good morning to everybody. So today we will talk about part 5, which is the geotechnical part of Eurocode 8. And you are here the outline of my presentation. The first question we will ask is, why do we revise part 5, Eurocode 8 part 5? Then I will give you just a very brief overview of the content of this document. And we will speak in more details about 3 topics: the basis of design, the method of analysis, which are recommended in part 5, the seismic action, and the soil properties. So why do we revise part 5? As a matter of fact, there are 2 sources for this revision. The first one arose from the CEN inquiry almost 10 years ago, where the comments from all member states came to CEN, and among these comments, the most important one were to reduce the conservatism of the force-based approach, they were used in the current version of, they are used in the current version of part 5, revisit the material factors, and develop section on soil structure interaction, piles, and retaining structure. Those were the main comments. Then we receive also comments and a mandate from the subcommittee 8, the Eurocode 8 committee, to develop a section on the seismic action on underground structures, and also to introduce, to be consistent with the other part of Eurocode 8, to introduce the displacement-based approaches as an alternative method of analysis to the force-based approach. These are the main sources, and these were in our mandate. So now I will give you a brief overview of the content. As you know, part 5 is only one chapter among the 6 parts of the Seismic Eurocode 8, and this is the only one which is related to geotechnical issues. It is a transverse document, which means it is applicable to part 2, for example, bridges, part 4, tanks, pipeline, and so on. So it's a transverse document that should cover new and existing structures, and also geotechnical system and geotechnical structures. I will define in a few slides what we mean by geotechnical system and geotechnical structures. Very important, but this is not really new. Part 5 complements Eurocode 7, EN 1997, for the seismic design situation. And it's not a substitute to this document. Just a complementary document for the seismic design situation. So just to give you the project team, you will see all the people today. Project team is listed here. In addition to the 6 members here, Philippe Biche, who is the chairman of SC8, attended all our meetings during the drafting of the document. So the table of contents, as you see, we have now 11 chapters in part 5. The first 3 chapters are common to all Eurocode. Then we have the basis of design, seismic action, ground properties, requirements for seating and foundation soil, soil structure interaction, foundation system, earth retaining structure, underground structures. What you see here is with the red star are the really new chapters. They either do not exist in the current version, or they have been significantly expanded and changed, like chapter 8 on soil-structure interaction. The chapter with the light brown star are those which have been really significantly expanded, as you will see. The chapter 6 and 7 were changed, of course, because the content is not the same, but basically they are similar to the previous version. We will cover in my presentation, I will cover only the content of the first 3 chapters, 4, 5, and 6. And this document is accompanied by 10 annexes. Just the purpose of these annexes was to provide the designer with useful information, mainly a lot of equations, and we did not want to put these equations in the main text, so they are provided in the annexes to avoid designer to look and go through the literature to find the correct answer. So the red star again are all the new annexes, and the light brown is the one which has been expanded. Just a word, all these annexes at the present stage are informative annexes, because they may evolve during time with new methods and so on. There is still one discussion about Annex G, which is the evaluation of earth pressure, which may become normative to be consistent with what is done in 2 other parts of Eurocode 8, the one on buildings, part 1, 2, and the one on bridges, part 2, but it's not yet decided. So with this very quick overview of the documents, let's enter into more details for the basis of design. So as I mentioned, part 5 is a peculiar document because it has to deal with geotechnical structures. What we call geotechnical structures are structures that include the ground or a structural member that relies on the ground for resistance. A retaining wall, for example, is a typical geotechnical structure because stability of the retaining walls relies on the ground resistance. slope, obviously, dikes are geotechnical structures. But we also have to deal with geotechnical systems. A geotechnical system, as we define it, is a complex system where one geotechnical structure, as defined above, interacts with other structures or geotechnical structures. Examples of those geotechnical systems are retaining walls with a supported structure at the crest, or a slope with a structure at the crest or the two, or a foundation of a building. These are geotechnical systems. And this classification, of course, has implications. If you look in terms of performance requirements, for example, and if we take a geotechnical system on the right-hand side of my slide, then the performance requirements are defined in part 1.1, and they are those of the structure. Of course, these performance requirements are a function of the limit states you want to check. The consequence classes of geotechnical systems and the associated return period for the design motion are typically the consequence classes and the return period of the structure. Now, if you turn your attention to geotechnical structures, the performance requirements of the geotechnical structure are defined in part 5. They depend, of course, on the limit states you want to check. The consequence classes and the associated return period are also defined in part 5 for geotechnical structures. So there is here a slight difference with the other parts of Eurocode 8. As you have learned in the last webinar, there are 4 consequence classes: CC1, CC2, CC3A, and CC3B. In part 5, for geotechnical structures, we have only 3 consequence classes: CC1, CC2, and only 1 CC3. And what you have, of course, the classification is an NDP, a nationally determined parameter. Each member state has to define in which consequence class you want to put such and such geotechnical structures. And the return period for the design motion associated with these consequence classes are those listed here. They are also NDPs. They depend on the limit state to check: non-collapse limit state, significant damage, and damage limitation. These values are NDP, as I mentioned, and it's up to each member state to define the value. But what you see here, for example, for the consequence class CC2 and the significant damage limit state, we have the classical value for the return period of 475 years. For the CC1 consequence class, the values are similar to what is defined in the other part of Eurocode 8. Now for the CC3, they are different because we have only 1 consequence class instead of 2 here. Seismic action class. As you know, the seismic action class is defined in part 1, and it's based on that coefficient, the seismic action index as delta, and this coefficient is used to define the zone, the areas of very low, low, moderate, and high seismicities based on this coefficient. This seismic action index is the product of 4 terms, and it's written here. S alpha, 475 is simply the spectral acceleration for the return period of 475 at the plateau of the response spectrum on a soil category A. F alpha is a site amplification factor, depends on the soil profile. Ft is the topographic amplification factor. So all these 3 coefficients are defined in part 1.1. Delta is an NDP parameter, and it's defined in part 5 for the geotechnical structure. Again, if you look at the geotechnical system, as we define them, the values of delta are simply those given to the structure, and they are defined in the relevant parts of Eurocode 8. For the geotechnical structure, the recommended value, which are again NDP, are provided here, going from 0.6 to 1.5 for the consequence class CC3. Method of analysis. Method of analysis. This is the classical one, which is used in the current version, which is a force-based approach where compliance to the performance requirements are checked in terms of generalized stresses or forces. But we were requested to introduce an alternative, which is a displacement-based approach, I would call it DBA now, where the compliance to the performance requirements are checked by comparison of the calculated permanent displacement to acceptable ones. In both cases, what we have to do is to check that inequality where EFD is related to the action and RD is related to the resistance. In the force-based approach, EFD is simply the calculated general stresses or forces, and the design resistance is the resistance of the system. In the displacement-based approach, EFD are the calculated displacement and RD are the allowable displacement. So in any case, we have to check that inequality. Let's focus a little bit on the design value of resistance. In the material factor approach, which is the preferred choice in part 5, the design resistance RD is defined from the resistance of the system here, where xk is the characteristic value of the material parameter, typically the end-range shear strength, for example, for a fine body soil. AD are geometrical parameters, and FED are the actions. It might be strange to see FED on the right-hand side of this equation here, but if you think, for example, of checking sliding of a foundation, the resistance depends on the action. Or if you look at the retaining wall, the resistance, the stability of the retaining wall depends also on the action. So in the material factor approach, we just divide the characteristic value of the material by this material factor gamma m. This approach is valid for both displacement-based and force-based approaches. In the resistance factor approach that we introduce here to be consistent with some approaches in Eurocode 7, the resistance factor approach, the design resistance RD is a function of the resistance of the system, but this time we define the global resistance by the factor gamma R here, which is the resistance factor. Be careful, this approach is only valid for force-based approaches. Just to be complete, the effect factor approach, with which some of you might be familiar because it's used in Eurocode 7, does not apply to the seismic design situation. The displacement-based approach can be implemented by calculating the permanent displacement either from a nonlinear static analysis, you do not need to run a full response history analysis, or from a response history analysis. In that case, you need accelerometers, and the selection of accelerometers are defined in part 1.1. But what we stress here is that you should use preferably natural recorded accelerometers to calculate your permanent ground deformation of displacement. We are conscious that Eurocode 8 part 1.1 allows the use of spectrally matched or artificial accelerometers, but we do not recommend their use to calculate permanent displacement. So, seismic action, this is something which is important. You know that the stability of geotechnical structures or systems involves large volume of soil, and therefore the seismic action is not uniform throughout the volume. You have variation due to spatial incoherence, variation with depth, and this should be accounted for if we don't want to be over conservative. Let's take just an example. What you know here from part 1.1 is the free field. Okay, you know S alpha which is the spectral acceleration at the plateau, or if you prefer, you know the free field P ground acceleration, which is the ratio between S alpha and FA. So you know that value. But if you look at the slope, this value AH here varies depending on the vertical where you are and depending on depth. Usually it decreases with depth. And if we use in our verification, the value at the ground surface, you see we may be over conservative. So to consider that effect, we introduce two factors. The first one here, the seismic action in part 5 is defined by this conventional horizontal ground acceleration, which is the product of the P ground acceleration in free field, times a factor beta H and divided by a factor TH. Beta H is the coefficient which is here to reflect the spatial variation with depth of the horizontal ground motion. Obviously, beta H varies between 0 and 1. This horizontal spatial variability is defined in part 1.1 in the relevant section, which is listed here. The variability with depth is applicable to both force-based approach and displacement-based approach. And the way you take it into account depends, yes, of course, on your model, the way you compute it, and the method of analysis. This beta H can be computed from a site response analysis or can be estimated from the Annex A, which provides the variation of beta H here as a function of one parameter. So you see beta H starts from 1, decreases down to, let's say, something of the order of 0.35. What you have in the axis here is something related to the height of the slope or the height of the retaining wall in contact with the soil, the shear wave velocity of the soil, and Tm, which is a characteristic period which characterizes the frequency content of the input motion. You can estimate it, calculate it if you want. It's not so easy. So we have a simplified equation here, which says that the Tn value is simply the sum of Tb plus Tc, Tb and Tc being the two corner periods that bound the plateau of the response spectrum. Now, we have another factor, as I mentioned, in this seismic action, which is TH. And TH, which divided the seismic action, is a coefficient that reflects the amplitude of accepted permanent displacement. Okay? And TH reflects the nonlinear soil behavior. Of course, it depends on soil type and on the structure and on the amount of acceptable displacement. Which is important to notice, if you use a displacement-based approach, obviously TH should be equal to 1, otherwise you would be double counting the effect of the nonlinear soil behavior. TH is only applicable to force-based approaches. Last topic I would like to cover now are the soil properties. So the first slide here is very known now. It is already presented in the current version of Eurocode 8. We say that the shear wave velocity, Vs, is the most reliable indicator of the stiffness of the ground motion for seismic design. What is new is now the way we define this Vs profile. Previously, I mentioned that we have different seismic action classes, very low, low, moderate, and high seismic action classes. For the moderate and high seismic action classes, a direct measurement of the shear wave velocity is required. While for moderate and very low seismic action classes, you are allowed to use empirical correlation to define your shear wave velocity profile. When I mean empirical correlation, it's correlation with other in situ tests like SPT, compenetration test, and so on. This table, I just show this table. You had such a similar table in the current version of Eurocode 8, but one of the comments we received during the inquiry is that our table was limited to a maximum shear wave velocity of 360 meters per second. Therefore, it did not cover all the materials you may be encountering. This table has been expanded. It gives the ratio G over G0. G0 is the shear modulus at very low shear strength as a function of the material, the shear wave velocity, and of course, as a function of the seismicity level. The higher the seismicity level, the more important are the induced shear strength, and the smaller is the second shear modulus. So this table gives different values. For example, if we take a moderate seismic level and a shear wave velocity between 250 and 400 meters per second, you see that the ratio G over G0 is of the order of 0.5. And the values in bracket below here, plus or minus 0.20, is just the range of value around 0.50 here, which represent plus or minus one standard, approximately plus or minus one standard deviation. You have another coefficient which is provided here, which is important. You will see that in the soil structure interaction studies, which is a fraction of critical damping ratio. And for this example I took, the value would be 7% or 0.07. Okay, so the table has been significantly expanded, but be careful, these values are very crude values and they should be used preferably at the preliminary stage. And when you enter the final phase of an important project, it will be better to measure those values. Now, with regards to the strengths, what is important to realize is that saturated soil should be considered to behave under undrained conditions. It does not mean that you have to make your study in terms of total stresses. You are allowed to make it in terms of effective stresses if you take into account, of course, the pore water pressure. Both approaches are allowed. If you look in terms of total stresses, for fine-grained soils or cohesive soil, if you prefer, the appropriate strength parameter is the undrained shear strength Cu, which should consider cyclic degradation effect for long duration earthquake, or even increase in the Cu due to the rapid loading rate. For coarse-grained soil, in total stresses, the appropriate strength parameter is the cyclic undrained shear strength, here, tau CYU. These ground properties are divided by partial factors. In the material factor approach, the partial factor gamma m, as we have seen, are applied to, let's say, the relevant value of the ground strength parameter. In the resistance factor approach, the partial factor gamma R are applied to the resistance. These partial factors, either gamma M or gamma R, are again NDP. Here, one important note. I have mentioned before that for the force-based approach, we have introduced this parameter TH, which is here to reflect the non-linear soil behavior. And you will see proposals in the next presentation for retaining structure, slope, and so on and so forth. Proposal for TH. It's important to note that the values of TH, which are recommended in our document, have been calibrated on the values of the partial factor that we recommend. Since the partial factors are NDPs, they may be modified in the national annexes of each member state, but in that case, the TH value which are provided in our document are no longer valid. They should be recalibrated with the partial factor retained in the annexes. These partial factors, you have on the right-hand side those which are defined in the current version of Eurocode 8, and on the left-hand side those which are proposed, the recommended values in the new version of Eurocode 8. For the end-range shear strength CU, we go from 1.4 to 1. For the drain cohesion, it was not defined in the current version. It's not defined in the current version, and we recommend a value of 1 on C prime. For the drain friction angle, the partial factor applies to tangent phi prime. It was equal to 125, now it's 1. For the rock unconfined compressive strength, we go from 1.4 in the current version to 1. For the end-range cyclic shear strength, this is the only one which is not changed. In the current version, it's equal to 125. Okay, it's not defined as a partial factor on the cyclic end-range shear strength. It's defined as a safety factor on the liquefaction resistance, but it's exactly the same. So it is 125 in the current version. We keep the value 125 in the present version. And the last two, which are not defined in the current version, we take one on the interface friction angle, if you want to check the sliding of foundation, for example, or on the global resistance factor when you use a resistance factor approach. Okay, with that, I will conclude my presentation. I thank you for your attention, and I'm ready for questions.
So thank you for the presentation. And we've got some questions. So I will start with the first question, which was given by Kostas Geropopoulos. So he's asking about the consequence classes. The consequence classes in Eurocode 0 have changed to comply with the consequence classes in part 1 of Eurocode 8. So we can found 4 consequence classes. So why Eurocode 8 part 5 defines only 3 consequence classes? And are these consequence classes completely compatible with Eurocode 7?
Okay, so I will start with the second part of the question. Yes, they are compatible with Eurocode 7, and we had several meetings with the project team from SC7, and we managed to have compatibility between the consequence classes of Eurocode 7 and Eurocode 8. Okay. Now, why do we have only one consequence class CC3? Simply because it was very difficult. You will see in a few minutes values which are provided, for example, for this coefficient TH, and they are very crude estimates of what could be the associated displacement and so on. So we did not feel that it was reasonable to be at that level of accuracy of providing different values for consequence class CC3A and CC3B. So what we took is something which is an average between both.
Mm-hmm. Okay, thanks. So the second question deals with the application of the displacement-based approach. And the question was given by Aishwarya Prabhakaran. And he's asking about the application of artificially generated accelegrams. So why they are not preferred to use within the displacement-based approach, and what are the consequences of using these artificially generated accelegrams? So if I remember well, there is a link to part 1, and I think that's the direction of the question.
Okay, the link to part 1 is here just to define, for example, the number of accelegrams you should use and the way you may choose them. Now, why do we recommend natural records? It's simply because artificial records, which are spectrally matched to the design response spectrum defined in part 1, do not represent real earthquakes, you know, and if you use those, you will calculate, of course, you will calculate displacement, but probably you will be over conservative and very far from reality, because in a real accelerogram, you have peaks and valleys in your response spectrum, and that may affect the behavior of a nonlinear system. So we really recommend that we cannot, of course, we cannot forbid the use of artificial accelerogram, but we really recommend to use natural records. It's not really an issue now. You have database of recorded motion which contains thousands of records, and you can find what you need.
Yeah, so maybe one complementary question from my side. So if you are using strong motion databases, extracting time histories, what about the scaling for these geotechnical applications? So are there any limits? Or?
We do not define any limit, but typically the state of the art or state of practice is you can use some scaling in terms of amplitude, not in terms of frequency content, of course. So you can use some scaling. Typically, scaling between 0.5 and up to 2 is acceptable. But it's not, I agree, it's not defined in the document. This is a state of practice in real life.
Okay, so there is a next question, I think not so easy to answer. When the revision of Eurocode 8 Part 5 will be available?
It's not up to me to answer. It's not an easy question. Okay, in next September, which means this year, the document I presented will be sent to all member states for the formal inquiry of SEN. Okay, then we will get back by early next year the comments, and we have, I think, and Antonio will correct me if I am wrong. Then we will have 1 year to implement the comment. But the final version applicable in each member state, the target date now is 2027, because all Eurocodes must be published at the same time. You know, in Eurocode 8, we rely, for example, for the geotechnical part, we rely on part 7. For the concrete, we rely on part 2, and so on and so forth. So all Eurocode will be published at the same time, and right now the target date is 2027. But for part 5, the inquiry period will be the fall semester, fall quarter. Okay.
Yes, Alain, if I can just
yeah,
complete your answer. I was checking here the exact date. So you are right. So for part 5, we are now entering the formal inquiry stage, where member countries will have the opportunity to propose or to suggest any changes to the current document. And then it will go through a period of changing, of translation, of preparation, and formal voting. And so all of those take time, and we have to do this for all the parts of Eurocodes, of all the Eurocodes actually. But so the foreseen date for the availability of all the Eurocodes, and all the Eurocode parts is August 2025, to send all these versions to the national standardization bodies, which will then have a period of about 1 year to produce the national annexes. And the foreseen date of publication, so of the publication of the second generation Eurocodes with the national annexes, is for September 2026.
Okay, a little bit earlier one.
Okay, so there was a second part of the question. So for the new hazard maps, so I think I can answer that the hazard maps are to be regulated on the national level. So they will appear later. So first of all, we have to finalize the Eurocodes on the European level, and then this is something that should happen on the national level with national experts.
But in part 1.1, you will have an annex with, which is an informative annex, of course, right, with the national, with the hazard map coming from the AEMH 20 project. Yeah.
That is right. So this is, let's say, a general map for all over Europe, quite helpful. But okay, so we can expect that on national level, probably some modifications will be made. But this is the first time that we have such an important map, of course. That's right. Okay. I personally have also one question. What I saw is that I think table 6.1 is really important for the practice. So I think it's quite easy to apply, and so such a table was not there in the former version. So my question is it possible to apply this table also to situations with soft soil situations with lower shear wave velocities than 250 that is given in the table?
We'll put the table here. Okay, here is the table. Now
yes.
Okay.
That is the table, yeah.
As you see from the table, we go down to 150.
Mm-hmm.
Usually we don't want to go at smaller value because we don't have enough data, and this is a very peculiar soil. It's very rare that you find a profile with a shear wave velocity which is smaller than 150. I don't say you cannot, but in that case you have better run a site response analysis to define your G over G0 and to make measurements. Okay. So
then you have to carry out the geotechnical inspection at site. So it's similar to what we had for soil class D in the former version.
Yeah, if you want. Yeah.
May I add a comment?
Yes.
It says for low seismic countries, it is allowed to extend this back to 100 shear for very soft soil.
I forgot.
It's just
okay.
Yes.
Only for low seismic.
But the limit is 100 then, right?
Yeah. Yeah, I see. It says yes. 100 is the lowest. Yes.
Okay. Thanks.
But once again, these values are very crude values, and you must be careful if you use it for a very important structure and so on. And you had better make measurements and calculate the values.
Of course. So if you have important structures, you should carry out some measurements. That's always better to have some investigations at site. But I expect, so sometimes if you have nothing, so you have at least a range. So what I saw, there is also a deviation that you have to consider. That's also quite good. Okay, so maybe one last question from my side. So I saw that you were mostly using SD limit state, right?
Yeah.
And NC was also given. Is it because of the link to part 3 or?
Yes, of course, because as I mentioned, we have to cover both new structure, in that case SD, the significant damage limit state applies, but also existing structure. In that case, it's a non-collapse limit states, and we refer to part 3. And you will see that the key edge values, for example, are given for all limit states.
Yes, I saw it. Yeah.
Okay.
Okay, so I will check the chat. So there are no further questions for the moment being. So I would like to thank you again, Alain, for the really well-structured presentation. I think we are now in the topic, and we can continue. And I will lead over to Tietjinde.